In this video, we're going to do an example where we're going to show a property about the first n integers and their sum. So once again, recall that the method of mathematical induction is to have two parts, a base case, where we show that property is true, the property is true for the first element in our sequence, the starting point. And then we also show, we want to show that for some k greater than or equal to our starting point A, that if the property is true for k, then the property is true for k plus 1. Right? And as we said before, we can do this with a direct proof. Where we suppose this first part and try to show, the second part. And this part that we suppose is called the inductive hypothesis. Okay, so we're going to do an example. We're going to take a look at the sum of the first n integers. And we're going to claim that the sum of the first n integers is n times n plus 1 over 2. So we can write this briefly in summation notation. The sum from I equals 1 to n of I, right, we want to add together the first n integers, is going to equal n times n plus 1 over 2. And an interesting thing, this has a little story behind it. This was first shown by a mathematician as a child. So Gauss was born in 1777 and died in 1855. Johann Gauss was given an assignment and lived in a one-room schoolhouse. And as an assignment, his teacher asked him to add the numbers 1 to 100. And the teacher was hoping for some time to rest and grade papers and things, and was really surprised when little Gauss came up with the answer inside a minute or two. He figured he had a little bit more time than that. And here's what Gauss did. So here's adding the numbers 1 to 100. And Gauss noticed that if you add the two outer numbers together, you get a sum of 101. And if you add the next numbers together, you also get a sum of 101. And this continues until you get to the very middle, where you also have a sum of 101. So what Gauss deduced is that the sum of all these numbers would be 50, because there's 50 such pairs, times 101. Don't know why I keep writing that. Which would be 5,050. Well, another way of writing this is to say this is equal to 100 times 101 over 2. Right? Because at 50, we're just, we could simplify this and cancel the 100 and the 2 and get the 50. And this, given that n in this case was 100, is the sum, or is n times n plus 1 over 2. So what we're going to do is we're going to prove this. So this seems to work really well here. Let's prove that it works in the general case. And to do this, we're going to do a proof by induction because we are talking about a sequence. Here it is a finite sequence, but I want to sum together the sequence starting at 1 and ending at 100. So again, we can rewrite this in summation notation as the sum of I equals 1 to n of I equals n times n plus 1 over 2. And this is for all n greater than or equal to 1. So we want to ask ourselves, where does this sequence start? N could be 5, it could be 100, it could be 1,000, it could be 1,000,000. What's the smallest number it could be? It's 1. So when we do our proof by induction, and again, you always want to label what type of proof you're doing. We're going to start with the base case. In general, we always start with the base case. It's not required. You do have to do both the base case and the inductive step. Both parts are required to do a proof. You could technically start with the inductive step, but I generally start with the base case. We're going to say let n equal 1. And recall, in the base case, our job is to show that the property is true for the first value. So we know what the first value is. The first value is 1, so we want to show that this property works when n is 1. So a really important thing to do is you don't want to just take this entire equality and plug in 1. And the reason is you can get some logic errors if you do that. So instead, and we talked about those errors when we did indirect proofs, I believe, or maybe it was direct proofs. But we've talked about those errors before. So instead, I'm going to approach this side by side. I'm going to take the left-hand side, and I'm going to take the right-hand side, and I'm going to address them individually. Okay, so left-hand side, I'm going to plug in a 1. So I'm going to have the summation from I equals 1 to 1 of I, which is just 1. For the right-hand side, I'm going to evaluate it where n equals 1, and I'm going to get 1 times 1 plus 1 over 2, which works out to 1 times 2 over 2. The 2's cancel, and we get a 1. So both sides gave me the same, evaluated the same answer. Which means our base case holds. Okay, and again, remember, it is really critical. You must evaluate each side separately. And we can show you, I'll show you in class, an example of where evaluating both sides the same can cause a problem. Well, actually, we already did that. We did that in a previous video, didn't we? Okay. So again, you must evaluate both sides separately. So we have our base case, and now we want to go on to our inductive step. I'm going to rewrite this. And notice here, I don't have to explicitly write for all n greater than or equal to 1. that's sort of implicitly included in this lower bound, saying we're starting at 1 and we're going up to whatever value. Okay, so our inductive step recall that we want to show again, let's go back and take a look here. Here we want to show that for some value of at least our initial value, we want to show that if the property is true for that value, then it's true for the next one. So we want to show that if our property is true, well, what's our property? Our property is that this relationship holds true. So I want to suppose that if I'm going to replace n with k now, right? If the property holds true for some k, well, there's my property with k, then the property is true for k plus 1. So let's write this out for k plus 1. So everywhere we had the k before, remember we replaced everywhere that had an n with a k. Now we're replacing everywhere that has a k with a k plus 1. And here we've got k plus, this other part right here has k plus 1. If I add a 1 to k, then I get k plus 2. All over 2. So we are going to want to suppose this in our inductive hypothesis. And we're going to want to show this. Okay. So we can say our inductive hypothesis, suppose and then we want to show that this works with k plus 1. Okay, so this is sort of where we're starting out with. You have to have an inductive hypothesis. I shortcutted it IH, but what that stands for is inductive hypothesis. And then you're also going to want to specify what your goal is. What do we want to show? One more important thing to note. I want to show this relationship down here. That means I cannot start with that relationship. Otherwise, I'm assuming what is to be shown. So I'm going to have to start with one side or the other. I could start with this side or with this side, but not both. I'm going to find it easier to start here. So as we said, we're going to start by looking at this summation. You can start looking at from the other side, right? You could start by looking at this side. That's just going to be a lot harder to work with. And my goal is if I start with this circled part, I want to then try to transform it and manipulate it algebraically to get it to look like this other part. And that's my goal. So I'm going to start with this, and I'm going to manipulate it and play with it and try to get it to look like that. So let's write this down on the other page. So our goal is to get, what was that? K plus 1 times K plus 2 over 2. Okay, so we're starting over here with our summation. And what can I do with this? Well, there's not a lot. I could expand it. I could do this. I could do that. But something that's going to be very, very useful is we want to look at our inductive hypothesis, right? We're supposing that this part right here, this relationship is true. This looks awful close to what I have. If I remove the final term here, we're going to be pretty close. So I'm going to split off the last term. And that last term was going to be K plus 1. And again, if this is a little confusing, try expanding our original summation, and hopefully this will make a bit more sense. This is by pulling off the last term. And now this part right here, we know what this is. By the inductive hypothesis. Right? If we look back, we say this relationship. And that's what we're supposing, so we can use it. Okay, so I'm going to rewrite this as saying this is equal to K times K plus 1 over 2 plus this K plus 1 over here that we can't lose. And it's really important to note that we're doing this by using the inductive hypothesis. Once we have this, it's just a matter of algebra. So I'm going to get like denominators. And then I'm going to combine the terms. And now notice I can pull out this K plus 1 here and here and factor it out and get K plus 1. And then I'm left with this K and this plus 2. And it's all divisible by 2. And we got all of these steps by algebra. And notice, this is what we wanted to show. So we're done. Our inductive proof is finished. We've shown that if we start with one term, this part that we're supposing right here, and we show that it can, if that's true. So we're not saying that we're just saying that if this red part here is true, if, not that it is, I'm just saying if it's true, does that mean that this next part is true? Yes. That's like saying if one domino pushes the next over, if one domino falls over, then the next one falls over. Combine that with our base case of knowing that the first domino falls over, or that this pattern, this relationship is true for our very initial point in our sequence. And now we know that the initial point will fall over, or the initial point is true, property is true. And that means from this step that if the initial point is true, then the next one is true. So the second one is true. And if the second one is true, then the third one is true, and so on. So we have proved, using a proof by induction, that the sum of the first n integers is n times n plus 1 over 2.